a specialized lab, and they employ dispensing opticians as well as some permanent resident optometrists. I think every trade has 2 to 3 eye clinic managers as well as 2 resident optometrists, and then the rest are filled with the students. So filling the train with students provide a huge educational opportunity for us at the universities. As Tanya said, there's 9 or 10 students. Currently, it's only 9 students. We've got 4 training institutions in South Africa training optometry students. So we try to send mixtures of UJ students and, for instance, University of Limpopo students together so that they can learn from each other. But also it is a learning curve that increases exponentially. Once you're on the train, you come there as a just past third year, early fourth year student, and now suddenly you are faced to see 20 patients, in total about 200 patients per day. And you can imagine the type of pathologies that they see. They learn exponentially. I see I get lots of nods from the students who's been there recently because you really get thrown into the deep end. If you can see, the testing stations are fairly basic. For us, it's fairly basic. For the students, it's basic. But for the population out there, for some, it is the first time they encounter seating areas with shaded areas over them. And we are testing. A majority of the trial is trial frame refraction, but there happens quite a lot in the cubicles as well, where there's fitted, I think, 3 or 4 cubicles on the train where they can test with the phoropters. You can imagine sending students from Johannesburg, KwaZulu-Natal, and Limpopo creates quite a lot of logistical issues, but also language issues. I've spoken some informal conversations with the 12 official languages. So when we send students from Gauteng up to KwaZulu-Natal, where most of these people are Zulu speaking, communication barriers becomes a huge issue. There's translators who's not trained in optometry, but between them and those optometry students, they often form quite a close bond, assisting them in the translation to test the patients. And as I said, they are there for about 2 weeks, and then they see an estimation of about 200 patients per day. And for those who like stats, these are the stats for this is our beautiful country. Gauteng being the smallest province, but also the most populated province. And here's just a breakdown of the statistics of how many patients they see per province. And we can still see Gauteng and areas like KwaZulu-Natal, which is supposed to be mainly urbanized, still see a lot of patients per year because of the unmet need. Also, which is quite a training or a learning experience for the trainer, the students, is the amount of pathologies that we see on the train. Allergic conjunctivitis, such as a vernal conjunctivitis, is rife across the country. So these are just the figures that they see per patient, and we can see in Gauteng, provinces such as the Eastern Cape and Free State, where there are dry and arid weather, vernal conjunctivitis is quite prevalent, but also identifying other things such as cataracts, bacterial conjunctivitis, and glaucoma, and have a specific referral system for those patients who don't get the necessary treatment or can't afford the private care treatment. Spectacle provisions, as I said, we try to prescribe ready-made readers or ready-made glasses. There's some plus glasses, there's some limited stock of minus glasses, but they do make prescription spectacles, made spectacles there, and you can see that almost fills the majority of those. Just recently in the clinic, last week, in fact, in the clinic, I saw a 7-year-old who walked uncorrected with a -7. He's 7 years old, he's a -7. That happens because the need is so great. I don't think it happened in most first world countries, but in South Africa, it is a common occurrence or a regular occurrence to see people who hasn't been having the opportunity to have the eyes tested and get to a -6 or a -7 by the age of 7. And therefore, the research around myopia control is so important because we can assist those children. So strategic significance, I'm going to give over to Tanya.
So the Phelophepa train allows us to have a, well, it's a scalable, cost-effective mobile health model. No, okay. So when we first started off as the eye care train, the idea was we had perfectly round frames, and we had drawers and drawers of all the different powers, and we could take the correct power out of the drawer, pop it into the frame, rotate it to the correct axis, and dispense immediately, which allowed us to dispense really quickly for patients that needed minus lenses and toric powers. Those that needed plus powers, we had all the ready-made readers already for them. And so we're not doing the round frames anymore, but we are able to reduce the costs for the patient, make it affordable. We've got patients that return every year when the train pulls up into their town. And it also reduces the pressure on the government facilities, the few government facilities that provide optometry. But in some provinces, I mean, the Eastern Cape, they've only got one optometrist in the main provincial hospital, servicing the entire province. So, you know, that can be an entire day's journey just to get to the provincial optometrist. So by bringing the train in, those patients are able to be seen much, much closer to home. And yeah, so 3 decades on, I can't believe it's 3 decades, because I was on that first eye care train. We have the Phelophepa train as a beacon of hope and a beacon of innovation. And we're able to then restore sight. We're detecting both vision, ocular, and systemic diseases, referring them correctly, and making sure that all those patients get treated.
Thank you, Tanya. Yeah, so Tanya was one of the first optometrists to work full-time on the train for a short while.
Yeah.
So, and all our students have been there, and it's still a beacon of hope, and it's still it's not necessarily annual, it's every biannual or twice every second year they get to the same station. And we see patients, you normally wake up at 4, 5 o'clock in the morning as the patients travel, because so they can get a space to have the eye seat tested. Sometimes you get patients who sleep over on the station so that at least they can get seen by the optometrist there. So just a question for the audience, as some of you are optometrists, but also some of you are definitely not. We would like you to share if there's initiatives in your country simulating this kind of train, or if there is a need for something like that, because the research that we've gathered from the VPO in terms of myopia control, in terms of keeping the right stop lenses, etc., will really benefit projects such as the Phelophepa train. Yeah, so Tanya has shared her pictures that she gave me an album, and I took pictures of the pictures just to show how it has changed, where they had to lean over to do the dispensing. Now there is stairs up there. The things have changed slightly. That used to be the train for those Dutch people around us, the eye care clinic, and that has changed significantly over the few years or over the past decade. For that. So that is, you can move on to the last slide. I think that's the last of us. So yeah, so that is just pictures of the eye care train and a picture of Prof. Yanni, who's known as the father of the eye care train. Thank you. We invite any questions, any discussions around that to see if there's anything that you would like to add. Just a very off the targets weird question when I saw Solani's bags. Tanya, these bags are absolutely awesome. And when I said, where did she order them from? She's not just a pretty face and a clever brain. She made these bags personally. I just thought I would like to say that because it is absolutely astonishing. So besides being one of the first train delegates, she's also not just a sharp brain, but also a avid seamstress. Thank you, Tanya, for that. Any questions, any comments?
So it's also true in the United States, the leading cause of visual impairment is a failure to have a pair of glasses. And the leading cause of blindness is cataract. So those, I mean, and you know, most people think of the United States very fluent, but we're not taking good care of the unfortunate. You know, and that's just a simple truth.
I think similar than South Africa, the United States is a vast country. So to get to the from the rural areas to the cities where there is maybe is definitely a problem. Thank you. Well, if there's no other questions, we'll move on. Thank you, Tanya.
Thank you, Ansunel. Oh, wait, there's another question.
You probably already told us the answer, but my hearing is so bad, I don't know if you said the answer or not. I'm just wondering who pays for the services? Does the patient have to contribute to the, or is it a whole public purse?
Thank you very much. So a lot of a lot of the initial cost was covered by Transnet, the funding organization of the whole mobile train. Then they had a partnership with Roche, who then assisted quite significantly with the funding. Most of it is coming out of the government fees or the government purse, but social responsibility from Transnet definitely funds most of it. The glasses were initially given out as a cost, at a cost for the patient, which was then, I think, 20 Rand per pair, which is half a dollar almost, $1, which is a dollar, which 20 Rand was affordable initially because they say it creates dignity and sort of a sense of paying for the service. Unfortunately, or fortunately, that principle has fallen away because 20 Rand for some people is a loaf of bread. It is feeding the family. So currently the glasses are dispensed at no cost. Funding through, it used to be the Lions organization, but there's funding and funding partners making it part of their social corporate responsibility. So yes, so funding is not necessarily just government purse. But the problem, as we've mentioned, is the public sector is so big and the government structures in the public sector is not serving most of the community. So initiatives, private funded initiatives such as Phelophepa becomes really significant.
One more comment. Thank you. I think this is a very inspiring project. As far as I know, WHO is now initiating a project called SPECS 2030, and the goal of this global project is to increase the coverage of refractive correction by 40% by 2030. And I am very lucky to be one member of that project. And actually, that project, I think the primary goal of this project is to help the people in undeveloped countries like Africa. So I am thinking whether obviously this mobile train based on the train system, of course, I am wondering whether the railways network is also well developed in other countries other than South Africa.
Thank you. Yes, I'll answer that. Unfortunately, the railway systems, even in South Africa, is not that well developed. When it was the 3-coach train, they could go into the small railways, into the small stations. With a 19-coach train, it's too big, too heavy. And the railway system in the rural areas where it was initially intended for is not sufficient to logistically to handle the train. So we were talking about something like an Africa by bus service, where we don't rely solely on a train or a railway system. The railway system across Africa used to be okay, but I think during corruption and bad management practices across Africa, it has fallen disarray. So currently, I think although the train was an awesome initiative and it's still very functional in South Africa, I think reaching the rest of Africa might be more practical using a bus service. So we were thinking of in the line of Africa by bus kind of service. Thanks.
Yeah, I wanted to say that that's inspiring, and I also remember some train, which in Mexico is called the train of health, also named as Doctor Wagon, and it is also a train going through some states. In Mexico, there are railways, not so much, not very well developed, but there is some kind of initiative. I don't think that I think that the trend you told us is older. I'm not sure how many years this has worked. And my question is as when the optometrists see some um, serious problem in the patient, the patient is referred to a hospital, or what is the process? Thank you.
Thank you. Yes, it is a difficult referral system because as the areas are mostly underserved, the patients, it's difficult to refer them. So basic treatment for vernal and glaucoma exist on the train, so they immediately prescribe where possible. But for cataracts, which is one of the leading causes of blindness, it is more difficult. So they do before, it's a big logistical issue sending the train to an area, because they do go and establish links with specific clinics, with specific hospitals, with ophthalmologists that's involved in eye care and cataract removal, so that there is a definite direct referral path. Because there's nothing worse than telling the patient, sorry, you've got cataracts, nothing we can do for you. So there is a definite, I think the train assisted with creating more referral pathways in the specifically rural communities. But sometimes, and I have to tell you the story, a granny comes there, she cannot do any needlework, and that was her basic income. So what they do, or read her Bible, which is what a lot of them do. So they do take a child out of school to assist her. So there's a child that now assists her and do the work for her, just by giving her a pair of plus 250s. Send that child back to school and provide the granny to get income. So it's almost a double reward. So there's a lot of those kind of stories that we hear every day when we go on the train, which, yes, although we will not be able to save everybody with cataracts and refractive errors, doing a little, I always say nobody made a greater mistake than he who said he could do little, do nothing by only doing a little. So doing a little goes a far way. Thank you. Thank you, everybody.
All right. Our next presentation will be by Alan Rubin, and he is talking on myopia and anisometropia, mirror symmetry, reflection, and quantitative analysis.
Okay, so good morning and welcome to South Africa. For those of you that haven't been here for a while like me, I'm probably the one here who's been here the longest while the pyramids were being built. That's when I kind of arrived. So what we're going to do today is basically I'm going to talk a little bit about myopia and anisometropia, and I want to talk a little bit about myopia and anisometropia, and more particularly looking at the issue of reflection, so that when we want to compare right and left eyes and do an interocular comparison, we have to worry about this issue of reflection. And if we look at, as you all know, myopia is a kind of huge problem globally, and the prevalence has been increasing quite dramatically over the last perhaps 30 to 50 years. And if you look at different parts of the world, the prevalence of myopia has kind of doubled or tripled or even worse. And here in Southern Africa, the estimated sort of prevalence here was about 5.1% or 5%. It's now estimated that by 2050, it's going to be here at about 30%. So a six-fold type of increase. And we seem to be spared somehow. If you look at this, the colors and so forth of this heat map, but essentially here in Australia, don't ask me why Australia, but in any event, 1 in 3 people who are estimated to have myopia by 2050 is a huge number of people in reality, and many parts of the world will be a lot worse than that. So if we want to understand things like myopia and anisometropia, and if we want to understand the methods that are being applied to try and slow down this progression, we need to make sure that we are analyzing the data using the appropriate methods. And we can do this either using power vectors, as Larry and his colleagues suggested in 1997, or the dioptric power matrix, which is from Keating and Bill Harris and other people. So the initial stage, of course, is we need to transform the information from sphere, cylinder, and axis to the dioptric power matrix, and do it using these equations. And essentially, we then can calculate from these entries here, we can calculate these coefficients. And these coefficients are essentially the same as what the rest of the world is using, which is NJ0 and J45. We call this thing the stigmatic coefficient. These are anti-stigmatic, and anti-stigmatic just means Jackson cross cylinder, basically. So this is a spherical coefficient, and this is a Jackson cross cylinder, and this is a Jackson cross cylinder. And we call this one the ortho anti-stigmatic coefficient, and this one is the oblique anti-stigmatic coefficient. And they're directly the same as MJ0 and J45. And we can use either the matrix, the dioptric power matrix, or we can use these power vectors for graphical and other purposes, basically. Now, typically these off-diagonal entries are equivalent, and so only 3 of these numbers are distinct. And so we can talk about symmetric dioptric power space, when in reality, if we think of a thick lens or we think of a contact lens, this is a thick optical system. And then, of course, these are not going to be equivalent necessarily. And so then you have four numbers, if you like, which are representing the power of an eye or the power of a contact lens. And then you've got a 4-dimensional problem rather than 3-dimensional problem. So if it's 3-dimensional, we talk about symmetric dioptric power space. If it's 4-dimensional, if it's 3-dimensional, then we talk about dioptric power space. If we think in terms of anisometropia, we can use ratios, for example, or we can use excesses or differences. And what we effectively are doing here is to divide the refractive error of the one eye by the refractive error of the other eye after we've done the transformation to the dioptric power matrix for each of the eyes. And this gives us a ratio. We kind of use the inverse in order to do this. You can also work out a difference, and we then simply subtracting the one dioptric power matrix from the other, and this allows us to compare the 2 eyes. And of course, if they're exactly identical, then the difference is going to be the null matrix, of 2 by 2 null matrix, essentially. So no difference, basically. So here's a very simple example, just showing you, if we look here, I've kind of said, well, let's imagine that these 2 eyes have exactly the same refractive error. And we've got anisometropia, and there's the measurement in clinical or conventional notation. We've transformed it here. And the little optical cross here is just showing you that this entry here is essentially the power in the reference meridian or horizontal meridian. This power here would be the reference power in the vertical meridian. And we can then work out the ratio, we can work out the difference here. And you can see here that because the two refractive errors are exactly identical, it's going to give you the identity matrix if it's expressed as a ratio. And there it is. And if we work out the difference, then we're going to get the null matrix here. And essentially that tells us there's no difference really between the refractive error of the one eye and the other eye. So that means we can then use things like these ratios. We can use excesses or the differences. And we'll also look a little bit this morning at comets, which we'll also use to examine this issue of anisometropia and myopia. We can do a starburst. And these sorts of things we kind of represent using stereo pairs. You don't have to use stereo pairs, but there are various reasons why we like this approach. But a starburst is essentially we're taking some kind of measurement, and that's going to then be the reference measurement, and that's either the mean, or it's an identity matrix or a null matrix, and then we're going to compare other measurements to that. And it gives us some idea of how similar are those measurements to the reference or to the, whatever we've chosen as the reference measurement. We have a whole lot of other methods such as polar profiles of dioptric power, which we're not going to really worry about for today. All right, so here's a typical stereo pair. So the first thing you need to do, I'm not sure if you're all familiar, I expect many people are, but if you aren't, what you need to be doing is looking in the middle here between the two halves and fixate on a point in front of the screen, so that what you get is a three-dimensional kind of percept in the center here. And again, if you're struggling, just look at your finger, put your finger on a pen here, just move it towards the screen in the middle. And you may see 4 at first, and then eventually you'll get to a point where you should see 3 and then three-dimensional. And once you have that three-dimensional percept, then basically just look at it and ignore the ones on the other sides. We don't really need to worry about those. All right, so that's essentially a stereo pair. And if you have a look here, what we've got here is a whole lot of red and blue dots. We've got the data here, which is from one of my postgrads who collected this data using this mobile portable sort of autorefractor and called the Netra. These are non-cycloplegic autorefractions. Essentially, I've indicated the right eyes with red and the left eyes with blue. And if you look at the two ellipsoids, or surfaces of constant probability density, look pretty much the same. The samples look pretty similar. And when we look at this kind of thing, we'll get into the details of it in a moment, but each of these surfaces of constant probability density will have a centroid or a center, and that is the mean of the sample, which we see indicated there for the right and the left eyes, basically. We also can represent it in terms of variances. And so, for example, you'll see these numbers here tell us that much of the data is varying in this direction. So there's largely spherical variation, stigmatic, we use the term stigmatic. And so largely there's spherical variation. Origin is emmetropia. These are your hyperopes up there. There's your myopes at the bottom here. And so this axis represents spheres, whereas this is an axis of Jackson cross cylinders. This is an axis of Jackson cross cylinders. And the further away a point is from that axis, the larger the magnitude of the cylinder, basically. And that's so we're able to look at these refractive errors and compare samples in this way. These variances, if you look at over here, we've got the stigmatic variance, we've got the ortho anti-stigmatic and the oblique anti-stigmatic variance, and much of the variation is there with very little variation in relation to the other axis extension. This is what this kind of information is telling us about the sample. One of the important things here is that if you look at, if you try and do a hypothesis test to compare the variances for the covariances for the two samples, you'll see here that the variances are unequal if you don't reflect the cylinder axis of one of the eyes, such as the left eyes. Whereas if you do the reflection, which we'll show and talk about as we go along, then the variances and covariances, these become equal. This thing is not different to this, provided we do that reflection. This is why this is important, because otherwise you're going to reach the wrong conclusions eventually when you start to do formal sort of testing of these kinds of situations. The means also, if the variances are unequal, you can't do the test on the means because it assumes equal variances. But if you do the reflection, because the variances are essentially the same, you can then test the means, and we find the means are not different here. So by doing the reflection, we're able to see, well, these two samples were not really different statistically at a 95% level of confidence, and essentially the means also were not different for these two samples. That's the same data that we've just been looking at for the right eyes. And here I've just shown you the left eyes without reflection and with reflection. And if you look at this, the green and the blue ellipsoids here don't seem to be very different. And the little cluster of points also for the right and the left eyes doesn't seem to be too very different. But in reality, lots is going on in terms of the reflection. Much of it doesn't show up quite so easy, as we'll see. But it doesn't show up so easy when you're looking at a plot like this. One of the ways we can see that there are these differences is using comets in the stereo pair. And you can see, for example, if we look at a measurement like this one here, the refractive error of the right eye is indicated by the dot. The end of the comet represents the refractive error of the left eye. And so for this particular person, you can see there was quite a big difference between right and left eye. Whereas if we look at someone like this, or we look at someone like that, there's almost no different. They had basically very little anisometropia, and they were essentially almost isometropia. This is kind of a bit messy when you've got all of these 279 comets, but obviously we can draw little clusters of comets and we can watch it on the monitor. We can see how this thing is developing and see exactly what's happening in terms of specific individuals. The excesses here, the origin would be, the origin is the null vector. And so there, for example, hidden away the origin of this plot, the stereo pair here, you can see that the mean excess is very close to the null vector. But in reality, we can see there are lots of eyes, such as this one, for example, where there's a big difference and there's lots of anisometropia. And that's basically true for many of these eyes, even though the mean might be similar, to the null vector, essentially. We can quantify things like the volume of the ellipsoid. This type of ellipsoid tells us that it contains 95% of the sample, and by implication of the population, if the sample is representative of that population. We also have another type of ellipsoid, which is this confidence ellipsoid on the mean. It's also a surface of constant probability density, but it relates to the average or the mean of the sample. And it gives us, again, an idea of what is the population mean and how similar is it to the sample mean. And, we have a certain level of confidence in making those decisions. Starburst, I mentioned that we can plot starbursts. In this case, the reference value is the mean, and then these are each the individual measurements. And again, if you fuse this thing, you'll be able to see that their lines, these lines are going in all different directions. And the longer the line, the greater the difference between the measurement that we're comparing to the reference value. So this is a very visual way of us looking at a sample and getting some feel. If all the measurements were very much like the reference value, then this whole starburst would collapse almost to a point, and we would see that, but we can see that's not the case here. All right, then in terms of ratios, without reflection of the cylinder axes for the left eye, and then with reflection of those axes. And again, you can see that now the origin would represent is the identity matrix, in which case the right and left eyes would have exactly the same refractive error. We can see that's not necessarily the case. And if you look at the axis length here, this is 50 diopters. And so I've done that deliberately because there's some of these ratios which are quite far away from that identity matrix. If we compare this stereo pair, this data here to this here, you can see that with the reflection of the axis of the left eyes, that although the numbers might look pretty similar, signs change, And there are various differences here in terms of what's going on in terms of these different component parts of the mean. We can kind of solve this thing here, and then we can represent it with a 2x2 optical matrix. But in this case, I wanted to show you where these things are in relation to where the origin is. And so this component type of interpretation helps to do that. Okay, so although the volumes and things stay fairly similar, stay basically the same, you can see that the orientation changes and the shape of the ellipsoid changes. And the centroids are not the same, even though the numbers look fairly similar because of the change in sign that you're seeing there, basically. All right, then I decided, well, okay, that's looking at some real data, so let's do some hypothetical data. I created a sample through randomization, where basically I decided let's go from minus 25 doctors of myopia to 2 doctors of hyperopia, and then also let's vary the SIL from minus 10 to 0. Minus 10 is probably a bit too much because I probably should have used minus 5, but 99% or 99.9% of people would not have a cylinder bigger than about would have a cylinder magnitude of greater than 5 diopters. But I wanted to actually emphasize the anisometropia particularly, and that's why I've kind of increased that cylinder value, the range a little bit there. All right, so initially here are these hypothetical eyes. Each little dot represents an eye. There's a 95% distribution ellipsoid for the data. The origin here is the null vector, essentially, and we can see then that the average would be Mopane. It's below the origin, and much of the variation is spherical. But there certainly are values, and again, this is 20 doctors from the origin. On each of the axes here, that's 20 doctors. So there are, you know, this if there was, this is just showing you the data essentially. We're going to get to the ratios and excesses as we go along. Here's the right and left eyes with and without reflection, with the red, blue being with the reflection, without the reflection, sorry. So just the data, the 500 right eyes, the 500 left eyes, and they look pretty much the same. Okay, then if I do the reflection and add in the ellipsoid, we've now got 3 of them here with the black one as well. You can see they all look, it's kind of messy, they all look pretty much the same at first glance. So here I'm just drawing the left eyes in blue, without the reflection in blue, and then with the reflection of certain axes in black. And so that's showing here, and the origin here is at the null vector. And essentially here, if you look at what's going on here, if we show a simple example here, where we're reflecting the cylinder axis, and we look at the optical crosses here, you can see that things are actually changing quite significantly with the reflection that we're doing with each of these eyes, even though the plot might not look as if that's what's actually going on. These comments also show you the left eyes with the end of the comment here will show you with the reflection, without the reflection there, and you can see that these refractive errors are changing quite dramatically in space. Just the excesses again, mean excess and volume. So there are obviously other alternatives. We don't have to necessarily use stereo pairs in order to look at these things. And so, for example, we can use Bland-Altman type plots. I think you're all familiar with the idea of these things. Essentially, we need to have 3 of them, one for what is M or Fi, stigmatic coefficients, one for the J0 or Fj, and one here for J45 or Fk, basically. The mean difference, of course, if we look at this value here, essentially pretty close to 0 in all cases. But we've got measurements here ranging from 20 diopters through to minus 20 or more than that. So there's lots of variation here in these excesses or differences. The limit of agreement as well, if you look at this over here, you'll see that this is almost, they're quite huge. If you look at these values here, I think there's a point, it's almost, what is it going to be? It's almost like 40 diopters or something like that. So so this is a huge limit of the width of this limit of agreement is huge. So this is another way of looking at these kinds of situations where you're looking at an anisometropia, trying to get a feel for whether there is or isn't an anisometropia. This last slide basically just shows us the situation where I've said, well, let's just take the right eyes and compare them to themselves. So obviously there is no anisometropia, they're all isometropic. And essentially here you can see you've got 500 little dots at the origin. In this case here, I said, well, let's take the right eyes, let's add in a little bit of random noise, and essentially we've got 1% on the spheres and 1% on the cylinders and 1% on the axes, and that's just showing you that there is, you know, these ratios now with the origin being the identity matrix. These ratios are kind of varying. You'll notice that the scale here has changed from 1 diopter to 0.05 diopter. So if we plotted this thing over here, it would look pretty much like what we see here. We wouldn't be able to see that there actually is variation. And the thing I was trying to show is you know, that this method helps us to see an isometropia and to be able to get a feel for how much an isometropia is, sense to quantify, which I haven't gone into any great detail, but you know, but we can quantify the data as well. All right, and then here I took out 2 outliers, and this is the original data, the left and right eyes. You can see it's 50 diopters from there to there. We've got a mean ratio here, which is quite near to the origin, but you can see that there are eyes where there's a huge amount of an isometropia in a sense, and they're far away from the origin. If you have a look at this one and you fuse this, you'll see that this is a kind of, this ellipsoid is varying mostly in relation to this axis and that axis. And this also shows over here by these numbers, whereas variation with respect to that axis here is almost 0. Covariances as well. This number is not 0. These are fairly close to 0. Again, telling us there's a linear relationship between variance in what would be M and J naught, or Fi and F. All right, so just to finish off then, essentially I'm just trying to show that reflection of cylinder axis is kind of critical or important in terms of analyzing data where there is myopia, where there is anisometropia, and that we can represent the differences, whether it's a distribution of myopia or it's a sample of an isometropia that we're looking at specifically, where we can represent this using these various methods that we've looked at, comments and so forth. And these things are important in terms of understanding the data. Never mind that maybe it seems very difficult, but probably not. Awesome. But it, you know, it helps us to understand the data and make sense of it. And in order to deal with refractive error and things like this, we've got to worry about stuff like reflection of cylinder axes. All right, thank you. Any questions?
Alan?
I'm supposed to know this, but I don't. So you spoke a lot about the volume. So that means if the quantitative value of small, it means there's less distribution. So if the volume is a higher number, it means that there's more variation in the sample. Is that what? Did I get that?
They're not exactly the same. But, sorry, they're not exactly the same, but they are related. And so the bigger the volume, the greater the variation. And the shape of the ellipsoid tells us what type of variation is essentially present.
Thanks.
Yeah, in looking at your stereo pairs, I was trying to visually gauge whether or not there are correlations between the anisometropia in the spherical component, the I term, and anisometropia in either of the 2 estimating terms, the J or the K. You didn't speak too much about correlations, and I was trying to ferret that out from just looking at the picture. Is that a reasonable way to go about it, or maybe we should do more traditional correlation graphs to tell me whether anisometropia is really a concept associated with just the eye term, or is there an astigmatic kind of asymmetry as well, or anisomo, astigmatism, I'm not sure the right word. If you understand what I'm saying, yeah.
Uh, the covariances that I didn't really spend a lot of time because of the limitations of time. The covariances are telling us whether there is a negative or positive correlation, linear correlation between the different parts. So you can look at the picture, and I guess you would be able to suss it out from the stereo piece, but we don't. We can look at those values for the covariances, and if they are 0, then it means there isn't a linear or positive or negative correlation. If we look at them, but we can obviously plot normal correlation plots with 2 of the components or even 3 of them and start looking at correlations in that way. So there are ways, but the variance covariance matrix already has that information in there. It tells us whether the stigmatic spherical variation is related to variation in, for example, J0 and stigmatic 1 image J0, for example. So that's already in there, but we could obviously explore it in more detail. That to help you with your question. Okay, anybody else? I must do like the students, huh? Okay, what's your question? All right.
Right, thank you, Alan. Our next presenter is Christina Mokoena. She is talking about ocular biometry across the African continent. Now, I just need to give you a little bit of background. As a requirement for attending Mopane VPO, I told all my students that they needed to put together a presentation, which is a little bit of a challenge when you just registered and haven't even got your ethics clearance yet. So I said to, I think it was 2 of you that you needed to do a review. So Christina is presenting a review.
All right. Yeah. Hello, everybody. My name is Christina, as Tanya has already said. So yeah, I'll be doing a review on ocular biometry across the African continent. So just a little bit of background. Basically, what was happening is that I am doing my master's, and the topic is basically the differences in intra-ethnic differences in ocular biometry. So we're basically going to be looking within South Africa. What is the differences within the ethnic groups in South Africa? So then what I basically did, I just went with something that I've already had and then did that. Okay, so be lenient. Cool. So what we're going to be doing is, what I did was a quick review on the ocular biometry. So let's have a look at that. It basically measures the axial length, the anterior chamber depth, the length, thickness, corneal curvature, and all of that. Okay. Why are we doing this? Is these measurements are essential for cataract surgery, and also when we're doing IOL calculations for the ophthalmic optics people. It also helps us, so when we do have the norms for each and every one of these measurements, it helps us to kind of gauge which one is
Hold it lower.
To kind of gauge which one, which people will be at a higher risk for certain diseases like glaucoma, and maybe more susceptible to higher refractive errors and so forth. Right. Why did I choose Africa? When I was doing my research, I noticed that we have an underrepresentation of the global data. So even though we do have some of the articles and some of the studies that have been done, I noticed that it is not as much as the other countries. So we're gonna be looking at the ethnic and regional variation in eye anatomy, right? So once we have that, like I said, we're going to be focusing just on African right now. So then we'll have population-specific norms. So like, let's say, for example, we'll be looking at Ghana and say, like, this is the axial length norm for Ghana, and then maybe comparing it with the norm to say maybe Ghana is more susceptible to have a higher axial length and so forth. Get the picture, right? So when we were doing the review, the study design, there was a review. The data sources that we used PubMed and also a Web of Science. For the articles to be considered for the study, they needed to meet a specific criteria. So we only looked at the African population. They needed to contain the ocular biometric parameters that I've mentioned, so axial length. So it needed to speak something about the axial length or the anterior chamber depth or the central corneal thickness and so forth. Right, they needed to be in English. The ages that were selected were from 20 years going up to 70, and no ocular conditions were supposed to be present. So all the individuals needed to be healthy, because as we know, when you do have ocular conditions, they tend to affect how the eye looks. So the parameters changes. And also in the time, the articles that were obviously selected were within the past 10 years. All right, so let's have a look at this. So basically, it's okay. Right, so let's have a look at this. For each and every area in Africa, 6 parameters were looked at. So that is your axial length, that is your axial length, your anterior chamber depth, your lens thickness, your CCT, your keratometer, and your Y-to-Y. Here I have outlined all the norms. And while we were looking at a lot of different sample sizes, because all the reviews and all the articles were very different, so we kind of wanted something that had more or less all of the parameters. So that's why you guys are going to see a lot of difference in terms of the sample sizes, but we kind of like comparing each and every one. And it's not ideal, but yeah, it is what it is, because we do have an underrepresentation of the data. Right. So I have outlined or rather highlighted what I saw to be a bit of a problem, or maybe falling outside the norm, or maybe like having that kind of a trend. So let's say, for example, in Ethiopia, 400 eyes were looked at. And as you can see here with the central corneal thickness, sorry. The central corneal thickness was slightly lower when you compare it to all the others, right? So, you know, with your central corneal thickness, when you have it a bit lower, then it mimics the high IOP. So then you can kind of like think with the Ethiopians, maybe when we do the IOP measurements, we're not getting a full indication of what is happening, maybe because their eyes are naturally thinner, right? So same goes here and here and here, whereby the lens thickness was a bit shorter, right? Okay. Right. From the graph, from the graph, you guys can see that there were differences in the axial length, anterior chamber depth, corneal curvature, and lens thickness. Yes, they were not that significant, but you could see that it wasn't one sample, it wasn't one representation of that. Right. So what we did notice was in West Africa, we had shorter axial length and shallower anterior chamber depth. So Western Africa, let's have a look at that. What I included, it was Nigeria and Ghana. So they had a little bit of a shorter axial length and a shallower anterior chamber depth compared to the other ones. Right. With that being said, they were more susceptible to have high risk for primary angle closure glaucoma and hyperopia. So, as opposed to people in the southern and eastern Africa, which is, let's have a look, southern and eastern, which is South Africa. Eastern Africa, we had, where is it? Sudan. We had Sudan. Right. So we had Sudan. When you're comparing it to your West Africa, we had longer incident length and a higher incident of myopia, as we've also seen with the other presentation that just went through. Yeah. Right. Okay. What are we recommending? We are recommending that we develop some region-specific ocular biometry standards. Also, when I was doing the review, I noticed that a lot of researchers mentioned the fact that it might be nice that we have anthropometric, this is a very difficult word, that word, data incorporated into our biometers. So like, let's say, for example, taking into account how the body structure is, and then looking at the ocular biometry data as well. So this will help us to improve refractive and cataract surgery outcomes. So then you will have tailor-made special surgery initiative, like maybe how to attack a patient as an individual rather than generalizing the population, as we have been doing. And it will help with population-specific screening and prevention strategies. So like if we have a norm that is specific for that population, when we do the screening, then you can see that is this person falling within the norm just for that population or not. Right. So we want to expand on the biometric data sets in the underrepresented regions. From what I was saying here, you might have noticed that all the countries were in. So here we had Sudan, and then here we had Nigeria and Ghana. Here, nothing. And down here we had South Africa. So there is a shortage of, what can I say, data in Central Africa. So maybe let's have a look at that and see how their eyes are relating to the rest of Africa. Thank you. Any questions? No.
Thank you. I think that's very interesting to get the biometry down. But I was wondering, you said there's a probability of a higher incidence of glaucoma in the people that have the short eyes and just smaller parameters. But was that actually seen? Do you have data to say that that's actually happening?
No. Right. So now, how we were looking at it, it was not, we were basically looking at how the axial lens influences the IOP readings. Not to say that we did a study whereby there was a correlation between the corneal thickness and the IOP. So there wasn't actually a study that I referenced or I did that had that particular. Okay. Anything else?
Thank you very much. Yes, I realize you're just first year master, and it's already quite brave that you stand here before all these people presenting it like this. I wonder if you considered maybe a bit the next step? How would you address that? How would you generate the data that you need to address your problem, the problem that you identified?
The problem of, sorry.
The problem of lack of representation.
Yes. So like, as I've mentioned before I started, that it was actually part of the reason why I went and did that was inspired by what I was doing is for my master's. So what we're doing is basically we're gonna be doing getting a lot of people in so that we can get biometric data for those people, even though for mine it's a bit regional. So then it will be like just for South Africa, but then I think it will help with the unicity of the data that is around the world as well, and kind of like have those norms as well. So like I'm saying, I urge you all, since you guys are all researchers and everything, let us get that data. Yeah, especially for Central Africa. Yeah. Anybody else? Thank you.
Yeah.
Thank you, Christina. Our next presentation is from Fortune Mkhata, and she is looking at an analysis of anisometropia among optometry students at the University of Johannesburg, and she's looking at a retrospective data set. Does anybody know what to do?
What's the problem? It's this one, then it's me, and then it's
You know how to get it to reconnect.
just unplug the HDMI or replug, otherwise.
You connect up 6 times already.
Uh, yeah, it's still maybe switch on the beamer. Switch on the projector, switch it off and on again. The remote is.
Yeah.
I just need to walk in the direction. That's what I have to make it work.
That's
It's like something said.
Need to walk in this direction.
Good afternoon. My name is Fortune, and Dr. Tanya has already mentioned what I'm working on, which is the analysis of anisometropia among optometry students at the University of Johannesburg. And I believe that a lot of us are now very familiar with anisometropia, and Prof had already touched that, but on a very high level. So yes. So I'm just going to go through a little background and rationale of what anisometropia is, which is the refractive error condition characterized by spherical equivalent error difference between the two eyes. So it's actually defined as a power greater or equal to 1 diopter difference between the two eyes, which is in spherical equivalent. And according to when I go through literature and also observing from our patients or patients that usually see that are presenting with anisometropia, you get to see that it's actually interfering with their binocular vision, it's hindering their stereopsis, and also increases the risk of myopia, especially if it's left uncorrected. And while the age-related anisometropia has been documented, we find that the prevalence and the progression in young adults, particularly optometry students, remains very underexplored. So it actually caught my attention. And very, very important that optometry students, or the study is done because it actually enhances understanding of binocular vision, refractive error management, the clinical skills, and ultimately leading to improved patient care and outcomes. So my main research question here was, what is the prevalence, the patterns, and also the trends of anisometropia among optometry students at the University of Johannesburg? And my main study objectives was to categorize the refractive symmetry patterns among the students, and also to just assess the temporal trends in the anisometropia from the year 2007 to 2024. And also Dr. Tanya also already mentioned that it's a retrospective data. So I have data from the year 2007, a little bit of a gap from 2012 until 2022, and then from 2011, and sorry. So I have a little gap. I'm going to go through that again. Yes. So it's from 2007 to 2011, and then 2022 until 2024. So there's a little gap there. So my methodology is actually an observational retrospective study. Already mentioned that it's taking place at the University of Johannesburg at our optometry clinic. I have about 358 data set or data from second year optometry students. And the data was obtained by means of a non-cycloplegic autorefractor reading of both the right and the left eye. And after having all the data, I then calculated my spherical equivalent using the formula SE is equal to N plus C over 2. And I went on to classify, of which I'm not the one that classified, but I went to use the classification that has been done already to actually classify the different kinds of anisometropia, of which isometropia is power less than 1 diopter difference between the two eyes, the mild, which is a 1 to a 199 diopter difference between the two eyes, moderate a 2 to 2.99 difference between the two eyes, and high, which is power greater or equal to 3 diopters between the two eyes. And this is what I came about when I was doing my analysis. I found out that in that 358 data set cohort, there was a presentation of an 87% of isometropia, which actually showed us the bilateral symmetry, that there is actually bilateral symmetry in our data. And then I got 8.7% mild anisometropia, moderate that accounted for 2.2% and high 2.5%. And when I then looked at the temporal shift, when I looked at my, I'm going to show you a graph. I have some few graphs to show you this. So from 2007, there was like a 5.1% anisometropia, and then fast forward to 2024, 18.5%, which is really a rise in the trend of anisometropia at the University of Johannesburg, specifically on optometry students. And the trend analysis, there's rise both in frequency and severity over time, with some extreme cases of about 6 diopters in those that were observed in recent years. And this is a graph that I was talking about. So when you're looking, okay, yeah. So when we started with the data, when this data collection was started, you see that 2007, you see a 5.1% of anisometropia, and this line is where I already mentioned that I had some missing data. So from the year 2012 until the 2021. So I have some missing data there. And I've already taken into account that this missing data might actually have given me some, or might have limited my results, or we have missed some maybe some trends or some cases of anisometropia. Then when we then fast forward to 2024, you can see there 18.5, somewhere round about there. So there's really a rise. There's really a trend, a rise, a trend in the rise percentage of anisometropia from the year 2007 to 2024. And this is also another graph that represented the count of participants per year. You can also see the that from 2007, there was really mostly representation of your anisometropia, your mild. But when we're now looking at, starting from 2011 going upwards, you can now see high anisometropia emerging like that, your moderate emerging like that. So which also then shows us that there's actually an upward trend in the prevalence of anisometropia amongst the optometry students. Then this is a scatter plot showing us the relationship between the mean spherical equivalent and the absolute interocular spherical equivalent difference among the students. So here you can see the clustered, the near emmetrope, which actually shows us that the difference is not so much on participants that are actually near emmetropes or lower myopes or hyperopes. But as soon as the refractive error gets greater, you actually get to see the difference. There's no more clustering like how we see in lower or near emmetropes. And just to talk about the clinical implications, so we also noticed that high anisometropia poses, or we know according to literature that high anisometropia poses embryogenic risk and also demands early detection. And when we talk about the educational insight, that we also, it's also an assumption that we having in the department that because of the number of emmetropes and also the number of strabismus or unusual eye conditions that are presented by the students in the optom program, we actually assuming that the department itself is actually attracting students with eye conditions. But I feel like it's also an avenue or an opportunity to explore more, maybe include other departments, so you can actually have a tangible and reliable data as to is it that we attracting students,
with eye problems, or is it a coincidence, or is it how it is? So the limitations, I already mentioned that I have some gap there, which might actually have, or I might have missed some important trends. And also the restricted year study, because we only focused on second years, or maybe if we then look at first year, third, fourth year, we might find something different, of which also provides an opportunity to further the studies and expand the studies in this regard. And also the gathering of data through the non-cycloplegic measures. So we also taking into account that while taking the measurement, since it's non-cycloplegic, behind the autorefractor, it happens that accommodation might have played a role, but again, not too significant to maybe induce anisometropia, not so big enough to actually give us the anisometropia trends or anything like that. And also, just to conclude, after my analysis, I actually got to find out that anisometropia is increasingly prevalent among optom students, and also my cases are very common. Moderate and high cases are actually emerging in the recent years. And also the findings actually underscore the need for routine binocular vision screening in young adults. Thank you. Okay, do we have any questions?
Yes, I want to ask a question which is not related to your presentation, but maybe of interest to the audience. Can you go back to the slide 11? Yes. From this slide, I noticed the percentage of myopia is very high in optometry students, which is kind of abnormal in South Africa, right? So my question is, number one, yeah, I want to understand more about the ethnic percentage in these optometry students. Are they white people or black people or?
So from the 2007, we had a lot of white people, but with so it's actually a very mixed distribution. So you can say half is white, but when you're looking at our data, and also from the 2007, there was like a lot of whites, very few blacks, but now it's like the other way around, more blacks than whites or Indians. So it's actually very mixed. So I actually looked into that to say, can I say whites, Indians, because I felt like that, but it's actually not, it was not really going to give me a good indication, because in the beginning, there was like a lot of whites, Indians, very few blacks, but now it's the other way around, more blacks and very few Indians and whites. Yes.
Actually, my question is from my knowledge. I'm from China, by the way. Okay, myopia is very high in our country. And the fourth in Africa, okay, the myopia prevalence be very low. Okay, especially in black people. But here, I can see a very high percentage of myopia. So I'm thinking, even in South Africa, for example, outdoor activity is no problem for you guys, right? So there must be some kind of a very heavy workload for the optometry students or those who are getting into the university. So,
or high myopes were attracted to optometry.
Maybe, yes.
Which is what I said. I feel like now it's more like an opportunity to maybe check other departments, so we can see, is it that
yes,
students are attracted to this program because they already have issues.
Exactly. And also, I would suggest you to record or to measure the near work for all these students. Yes, to see whether near work is extremely high for the students here.
Influencing the refractive error. Yes. Yeah. Any questions?
Thank you, Fortune. It's not a question, it's more a comment. Me and Tanya had the conversation last night about hyperopia in our black population. Not being involved in refractive error research, but more clinical involved, I notice in the Black population, specifically in the school children, a high prevalence of hyperopia. So I ask Tanya the question, is it just my clinical perception or is it a true researched fact? So I want to say, so in terms of the student population has changed significantly, as you've mentioned, where we had a majority of white students and then into the ethnicity change into Black and more Indian students. Is that not also playing a role in the anisotropia change, or is it just due to the type?
So we can assume that Black people don't really do the eye test regularly or deal with things like your anisometropia at a very young age, only discover when they're now older or maybe getting into university. So it might assumptions, but not something that is recorded in literature, which I feel like we need to take a look into that. Thank you. Any other question?
Thank you. My question is regarding the classification of your anisometropia, and I just wanted to find out if whose classification did you use, and if there are any other classification that we can use to classify anisometropia. Thank you.
So the one that I use specifically is the one done by Vincent et al. In a study on myopic anisometropia. So there's different classifications, but it's not very variant. Like some will say less than 1, some will say 1 to 1.99, some will say 1 to 2. So, but it's almost like those classifications. Yeah. Other questions?
Thank you, Fortune. I think with us running a bit late because of this morning, we're trying to just keep track of our program. Let's have a tea and coffee break. I see it's already at the back. And if we can start again at 1 o'clock. Thanks.